Hello everyone, welcome to AI Anytime channel. In this video, we are going to look at a very interesting topic that's called prompt compression. If you have been working with large language model, you will be probably familiar with prompts and different prompting techniques. Now, prompt compression or prompt optimization is the need of the hour when it comes to large language models and the associated applications that we build. Now, there are different techniques that helps you know, uh, compress or optimize prompts. So in this video, we'll look at LLMLingua. It's a new technique, or it's like a project that has been created by Microsoft, and they have open sourced this. And we'll see that how we can use this library LLMLingua, and also how this can be used through orchestration frameworks like LangChain and Llama Index that helps you optimize prompts or compress prompts. Now, optimization might not be the appropriate word. Compression is the right word, so we'll call it prompt compression, and that's what they also call it. They say designing a language for LLMs via prompt compression. Now, I'll tell you why compression is important. It is important mainly for the token cost. Once you deal with the closed source models, like for example, OpenAI families model, or the Anthropic, or the AWS Bedrocks, or the GCP models, they are like they are a bit costly when you use like the likes of GPT-4 and Claude, the 200K context tokens. They are a bit costly, and the token cost can go high depending on the prompt frequency and the prompt's length. And that's why this helps you simplify the token complexity, prompt compression techniques, and that's what we are going to look at it. It's now really a need of the hour, mainly in the enterprises. If you work for an enterprise where you're working for multiple clients, they will probably have these mechanisms on their roadmaps that how you can help them reduce the token cost, because it's not only about the efficiency gains but also about how are you saving cost from the technology development standpoint, and that's why it is important. Now let's jump in and start seeing that how we can use LLM Lingua to build some of these in our capabilities. We'll use Llama Index because LLM Lingua has been integrated within Llama Index as an orchestration framework, and we're going to use that to see for some of the RAG kind of a system. So let's jump in and see how we can build that. Now, if you look at on my screen, it says LLM Lingua, designing a language for LLMs via prompt compression. Uh, it says LLM Lingua paper. There's with a code, and there's a Hugging Face demo. Now, if you come down, they give you an abstract. I will probably cover a bit the techniques that they use, like coarse grained compression and fine grained compression. Okay, so we'll cover that in a bit. Now, if you look at here, what's the real problem? Once you have increasingly longer prompt, in context learning or chain of thoughts or RAG, retrieval augmented generation, the co-pilots, the tools, agent, blah blah blah, right? If you have more than 10K or 20K tokens, when you pass this to a large language model, the challenges are many, like high latency, because we'll be including multiple calls to the API endpoints, right? There'll be concurrency, there'll be latency issue. Now, most of the models have limited context window where you cannot send more than 8K tokens, for example, or 16K or 32K tokens. Now, Anthropic Claude has 200K as well. That's pretty impressive. Now, most of the time LLMs issue with forgetting the context. They ignore the middle context. That's the real challenge with lost in the middle. I have a couple of videos on LIM, lost in the middle, that the LLM's problem. Hefty cost, because if you see the difference between GPT 3.5 and GPT 4, the cost is like this, it really make people scared, and that's what it is. How to efficiently utilize limited tokens while retaining and enhancing the information content in the prompt. That's what Lingua does, LLM Lingua. Now, it has both LLM Lingua and long LLM Lingua. Okay, both the papers are available here. I'll give the link in description. You can see this is for LLM Lingua and this is for the long LLM Lingua. You can find it out over here. Both are for Microsoft. They are pre-print available on Archive, and they are right now under review. Okay, so they are not this paper is not published. Long LLM Lingua. This is published there. You can see, it has been published. It's also the pre-print available on Archive. Now, this is where they explain the paper. I will explain pretty much high level that what are the techniques that they have been using. I will cover that. If you read here somewhere that they will explain that the things that they are using, and there are a lot of examples with RAG, the COTs, and etc. Now my focus is to see that how you can use it programmatically. So let's jump in and see that. Now I'll come here and I will start importing the libraries. So let me just first install. So I'm gonna do pip install, and you need GPU by the way to use if you are using this. You can see I'm on V100 Colab Pro because it's going to download an open source model. I will show that the model weights. V100 high RAM. I'm connected on Colab Pro. I'm gonna download Llama Index. So let's install Llama Index and LLMLingua by Microsoft. And once you install that, it will take a bit of time to install. Now, meanwhile, I'll have my OpenAI thingy done. So import OpenAI, and then I'll have OpenAI dot API key, and here I will set my API keys. So what I will do for that, let me just go to OpenAI keys and get that. Anyway, I will delete that once I complete my video. Okay. So API keys, I'll create a new Lingua demo, create secret, copy, and then just close. And I will just paste here, and I have my keys here. Now the next thing is that we need a data because we're going to do a RAG implementation. So we're going to implement a simple retrieval augmented generation pipeline here using Llama index, and that's where I will show that how you can use prompt compression techniques to get the similar or even better answers, and that will help you save some tokens and ultimately the cost associated with it. Now for that I have my this is the data that I'm going to use. I'll show you. It's an essay. Let me just get through wget. I'm using wget to get this file from Dropbox. Okay, and you can see it's get the file here. Let me just refresh it. And once you refresh, you can just download it, and I'll show what we are doing here. Okay, once it downloads, let me open that. And this is the essay that we have. This is an essay basically what I worked on February. It explains everything here. The essay you can read about it. It's pretty big by the way. You can also use PDFs. It doesn't matter. You can use PDF, but I'm using Paul Graham essay, and I've saved it in paulgraham.essay.txt. Now that's the file that I have used. Now there should be a logic, guys, that how are they using, what are the techniques that they have been using. So they use coarse grained compression through document level perplexity. Let me write it over here. So I'll add few cells and I'll first explain that what we are doing here. So let me just add a cell on top and how they are doing this prompt compression. So prompt compression by LLM Lingua. Okay, now the first is that they use is pretty much that we have seen with the likes of let me just write to the one first is chorus grained uh, compression through document level perplexity. I think I was among the first few YouTubers who created a video on perplexity and burstiness once there was a rise of ChatGPT, that how you can at least find some patterns if that's an AI generated tokens, right? That's where perplexity helps, because I will tell you that what does that mean. The second one is fine grained compression of the remaining. So it has two steps. The first one is coarse grained compression through document level perplexity, and the next one is fine grained compression of the remaining text using perplexity. Now these are the two techniques. Now I'll tell you that what does this mean, right? Coarse grained compression involves reducing the length or complexity of a text document as a whole. So basically it looks at the document level perplexity. It first summarizes it. It measures how well a language model predicts the given text in a document or predicts a given text document. Now perplexity is a measure That's basically used in natural language process to basically quantify how well a probability model predicts a sample, because most of the LLMs that we have seen, or the language models, they are all autoregressive models, okay, and they are probability model that predicts a sample. That's a token, by the way, and that's where perplexity helps, right, in measuring those. A lower perplexity indicates that the model is doing better. That's what it does. Now the coarse grained compression means, you have a document, makes it summarize, and then you use perplexity on a document level perplexity to measure that if that summarization is correct, a coarse grained. Now imagine you have a document with several paragraphs. You have a document which has around 100 of paragraphs, right? Coarse grained compression summarize these paragraphs into shorter forms while maintaining the overall context and meaning. So there is a contextual understanding. Once we perform this step, there should be that context. Now this is not the only step, because if you do this task, or if you perform this task rather, there will be some scenarios, you know uh, that some or a specific portion of the paragraphs, the summarized paragraphs, or often at the tokens level, okay, on the tokens level, that it might be missed. That's you need token perplexity, not the document level perplexity. You have to narrow it down to token level perplexity to, for individual words or token within the text. That's where the second step is, which is fine grained. Like once you perform the first step, then you perform the second step, which is fine grained compression of the remaining text using perplexity. That's what we are doing in the second step. So yeah, basically it looks at, I'll not say it's very similar to what entropy is. Once entropy is associated with a token, I think it's a bit different, where we use a masked language model to understand the context of the left and the right of the tokens, to see that if you can remove some of the tokens from the prompts. That's basically a bit different, but might be correlated in some way. That's what I'm thinking, right? But yeah, this is what it is. One is on document level. Once document is summarized, it basically makes your prompt shorter. Then you have the fine grained compression. It looks at the tokens within the text, okay, to find out if that token is relevant or required. Otherwise it will remove the token as well. So that's what on a very high level it does, guys. Both That's the technique that they use if you go through the research, but very high level, it's a very technical topic to understand. And I have some videos on perplexity. I'll give the link in the description. I have a 2 or 3 videos on perplexity, that how you can calculate perplexity score for a large language model, and also for the RAGs. Okay, there are some evaluation methods that we use, for measuring the perplexity. Now this is done. Now once this is done, we're going to use llama index. If I hope you have used llama index. If not, I will explain that. Now we're going to import a couple of things here, more than a couple of things. The first is the vector store. So let me get vector store index. Now the first is vector store index. The second is simple directory loader. Okay, so reader, by the way, excuse me. Loader is in LangChain. Simple directory reader. And once you have simple directory reader, you're gonna use load index from storage. Once you save that, you're gonna load that as well. Load the index. So load index from storage, and the last thing is storage context. That basically helps you with your vector store. Storage context. Excuse me. Yeah, storage context. Yeah, that's it. Now we are done with our llama thingy. Once you are done with your llama thingy, what we're gonna do next is we're gonna load the document here, guys. So let's load the document. So I'm gonna say load document, and inside the document, the first thing is documents equals simple directory reader. Now in simple directory reader, what we are going to do is I'm going to have my input files, which is a list, by the way, that's defined as a Python list, where you can pass n number of input files. Suppose, for example, in a directory, if you have 500 files, but you only want to give 100 of it, you can also specify that explicitly. That's where input files helps. Now input files, I'm going to name that file here Paul Graham, excuse me, Paul Graham essay .txt. Now this is a file, and that's going to say load data. Load data. It will automatically find out the which is a txt, by the way. Now you have your documents. Now once we have your document, what I'm going to do is to create index. So index equals vector store. So let's do that. Vector store index, and vector store index, I'm going to do dot from document. If you remember, if you use LangChain, you do chroma dot from documents, flash dot from documents, Waviate dot from documents, so on and so forth, right? With different vector databases available. Now from documents, because you are creating a document, that's where you are using it. If you once create it, you don't have to use this. Now vector store index dot from documents, I'm going to pass my documents here. So let's do that. So documents, and then I'm just going to create the index here. Now once we have the index, what next we have to do is we're going to look at retriever. So let me just write retriever equals, you can see here that has been done. Now retriever and retriever equal to index dot as retriever. Very similar to LangChain, guys. If you have worked with LangChain, and then here you can pass your similarity top k documents. Okay, so similarity, and I'm gonna get at least 10, and that's where the problem is, right? When you look at Lost in Middle, a research done by Stanford, okay, where they say LLM struggles with your middle context. If you have a large context, it looks at the first and the last context or the page content or whatever you name it. It ignores in the middle. And I have created n number of videos on Lost in the Middle, how to use re-ranking features or the flash re-rank or the Waviate or the Coher re-rank, cross encoders, etc. etc. Go ahead and look at those videos. I'll give the link in description. That will be helpful. Now here retriever equal to index dot as retriever, similarity top 10k. Let's just get it in here. Now once you do that, the next I'm going to do is question. So let me first ask a question. So question equals, and here I'm going to ask my question. So let's have a question. Uh, where did the author go for art school? Okay, this is related to a school, art school, etc. Right? That's why I'm asking this question. This is a question that I'm asking. Now you can have your own document. Now the next is context list, and I'm passing my context list equal, which is a list n dot get content. That's what I'm gonna using, because we have top k equals 10. We don't need all of this for n in context. Perfectly fine. This is what we need, and then length. But then we need the context. I forgot to call the context. Question answer. We should know the answer. Okay, the answer for this, there should be a ground. There should be the ground truth, which is your answer. This is correct. The answer for this is RISD. This is the school name, by the way, RISD. So let me just run this answer. And after answer, once we have your question and answer, then we need the context. So what you are doing here, so we have a question, because in the RAG, what we do, you have a retrieval first that retrieves the relevant chunks based on your prompt, which is combined with your question. So we have the question, we are now have the real answer, which is the reference RISD, and then we are getting the context from which LLM will generate the answer. Now the context equals retriever dot retrieve, and then only passing the question, not the answer here. Okay, the answer is for us. So context equal retriever dot retrieve, and now I'm gonna use context list here. So n dot get content for n in context and the length of context. So let's get that. So context list, and you can see 10, because we also specified here 10 similarity top k. Now we have defined similarity top k as 10, and we are getting 10 here, so that is working fine. So this is okay. Now the next thing that we have to do is, let me add a few cell here, and let's get OpenAI. Now the retriever is done. We are moving to the generation part of it. Now from LLMs, very similar to LangChain, where we do from LangChain.LLMs import Azure OpenAI, whatever, right? Chat OpenAI or whatever you import it. Now import OpenAI here. So from llama index LLMs, we are getting OpenAI. Okay, and an LLM equals, I'm gonna pass my OpenAI, and in OpenAI, I'm passing models equal. I'm gonna use GPT 3.5 Turbo. So let's use GPT 3.5 Turbo, and I'm gonna pass 16K, because then we are looking at the larger context to evaluate. 16K model I'm using. Let's first print the LLM and see the pipeline. You can see this is what the LLM we are using. You can find it out over here. Temperature is by default 0.1. You can set all of this, the inference parameter, you can set that. Okay, now let me, oh, okay, again I'm running it. Now after that, what we have to do is, let's have a prompt thingy. So prompt equals, I'm going to do a double of line break, excuse me, line break dot join, and in join I'm passing context list, and then I'm passing question. Now this is my prompt. Now response equals LLM dot complete. And let's remove max tokens. We don't need that. Okay, for now. So prompt, and let's print the str response, the string response. And you can see the answer is the author went to Rhode Island School of Design, which is RISD for art school. Now you can find out the answer was also RISD. This is for us to match it. So you can see that the answer is right when we are using the GPT 3.5 Turbo 16K, which is a normal, a self-query retriever kind of a RAG where you have a vector database, you have a vector store, by the way, you have a vector store, and you are looking at. Now we haven't, till now we haven't used the prompt compressor. It's happening how it happens. Now we'll move to the prompt compression part. So let's do that. Let me add a few cell thingy here. Okay. Now let's set up LLMLingua. Okay. So I'm gonna set up LLMLingua here. Set up LLMLingua. How do we set up LLMLingua? First, let's get all the required dependencies here. Query engine. I'm going to use import retriever query engine. Retriever query engine. This is fine. The next is we need the, like if you have used LangChain, then you get the chain type stuff, map, re-rank, etc. Right here we need the response synthesizers. We need response synthesis. Okay. Now from llama index dot response underscore synthesizers, you can see it's suggesting me now, and then I'm going to use compact and refine. That is fantastic. Compact and refine. Okay. I need long LLM lingua, so let's get that. So I'm going to say from llama index, excuse me, there's something wrong. From llama index dot indices, it's in the indices, and post processor, it's a post processor thingy. Why it's not suggesting? Yes, it's suggesting me now. And then I'm gonna import long. Hopefully it should show me that it has something. Yes, correct. Now you can see it has two things. One is the long context reorder that solves the problem of lost in the middle. That's basically a re-ranker. It re-ranks your retrieved chunks or the context. That's the exactly same thing in LangChain as well. That's called long context reorder. But here I'm interested in long LLM lingua post processor. That's what I'm interested in. Now let's get that thingy. Now once we do that, here we'll initiate that. So let's have a variable called node post processor. And you can see it says, okay, inside this, you do all of your magic. And I'm going to do all of my magic. The first thing that I'm going to do is instruction. So let's define an instruction string. And in the instruction, I'm saying, given the context, please answer the final question. This is my instruction to the model. Okay, this is the instruction. Then I'm going to target the token. Now suppose, for example, if you have 1000 tokens by default with your prompts and the question that you are feeding right now, if you want to compress it, you can give a target token. For example, what is the value that you want to bring it to? So I'll say, okay, if there is 1000, let's bring it to 300. Okay, so let's do that. So target token, and I'm saying target token equals to 300, which is an integer value. So let's do that. Now after target token, you can see the model name, by the way, it's using llama 27b HF. Make sure if you are on, if you have to use llama 27b HF by default, if you want to use some other models, you have to look at the compatible model, the compatible local LLMs. By the way, by default, it's by Nous Research Together Computer, Nous Research llama 27b HF. Okay, so by Nous Research, I'm using that llama 27b HF. Let's do that. Now, what I'm going to do the rank method now. So let's define a rank method. So make sure, guys, you don't use a closed source model again to compress the prompt, because it doesn't make any sense, because again you'll be doing the same mistake again to increase the token cost. You need a local LLMs or LMs or some domain specific prompt LLMs that will help you compress or optimize the prompt. That's what you need. Now in the rank method, I'm saying, okay, you use the long LLM lingua. Okay, so a long LLM lingua, this is what you're going to use. And after that, you need some compressed quarks. Okay, the additional arguments or the quarks that we use. So here let me just use additional. You can see it suggests here as well additional compressed quarks, and it's a key value pair. It's a dictionary that it takes it. Now the first thing is condition. So let's do condition compare, which let's make it true. Of course, we need to compare with. So true, let's make it true. Now after that, condition in question. So condition in question, that will be after. Okay, so condition in question. Hopefully it is, I spelled it right. Condition in and let's keep after. No, that should not be capital by any mean. That's all small. After condition in question, and after that context budget. What is the context budget? So it should be like, it's again an integer value. So let's integer, when I say the number is by say string, but the number is something that you have to keep in mind, that what is your context budget, the context length that you have. So context budget is plus 100, and after that, do we want to use reorder? I say yes. So reorder, let's sort it. So reorder context, I'm gonna say sort. Reorder context sort, that's basically enable the document reorder. That helps you with LIM as well. And then you have a compression ratio. So let me just do a dynamic context. uh, that should be dynamic context. It's not showing me. It's okay. A dynamic context compression ratio, and it's again a value, so 0.3. Hopefully this should not give me an error. If it gives me an error, it's a trouble for me. Then I have to look at the documentation for this. If I make any typo here. Now you can see it's now basically downloading your model, okay, and it will take a bit of time because it's 9.98 gigabytes. One safe tensor model weight. The other will not be around that big. The other one will be the 3 point something. You can see the downloading SAR, the SARted model weights of it, and it will take a bit of time. Once it's doing it, guys, let's write the next piece of code. So what I'm gonna do is, I'm saying, okay, let me add a few cells quickly. I'm saying retrieved. So let's call it retrieved nodes, and then gonna use retriever dot retrieve, and I'm passing the question. That's my retrieved node, and I'm gonna use a synthesizer. So synthesizer, and synthesizer equals, and I'm gonna pass compact and refine, and say, hey, look, compact and refine, and in this just use everything as default. So let me just write it here, and once we do that, we're gonna use this. Let's get query bundle. We need a schema for that. So from llama indices, this will be something in indices dot query dot schema. Hopefully I don't need query schema, I need query bundle. Import, let me see, query bundle, correct. I cannot run it right now because the above one is running. You can see the model has been downloaded. Now it has to be loaded, so it will take a bit of time. Now from llama, it is fine. Now we have to post process or compress using the synthesize. So let's do one thing. I'm going to say new retrieved, uh, new retrieved nodes equals correct. I'm going to use node post processor dot post process. This should not be retrieved. Let me see, post process nodes. Yeah, I need post process nodes, and here I'm going to pass my retrieved, correct. I'm going to pass my retrieved nodes query bundle. The query bundle is question. That's not question. This is completely wrong. This is not how it takes the input args. Okay, this is your query string. Query str equals, and then you pass your question. Okay, so this is what is, and then I don't need this synthesizer. Okay, now this is your new retrieved nodes. Okay, now new retrieved nodes. Okay, you can see it's still running. Let it run. Now once that is done, then I'm gonna write for original context. So let's do original context. Original context equals, then double of line breaks. I always make that mistake. Line break dot join n dot get content for n in retrieve node. This is right. I think this completely is right. N dot join n get content for n. Perfectly fine. And you can see it's still not loading. Okay, fine, your GPU will be utilized very soon, brother, don't worry. Original context is fine. Then we need the compressed context. Okay, so the compressed context, the compressed one. Now compressed context equals, join dot n get content for n in new retrieve node. This is perfectly fine. This is the right one, right recommendation by generative AI in Colab. That is done. Now let's get the original tokens. Okay, so what I'm gonna do is original tokens equals node post processor dot underscore LLM lingua, yes, dot get token. Where is get token? Yes, get token length, perfectly fine. This is what I need. And then I'm gonna pass my original context. And then you have your compressed tokens, node post processor dot LLM lingua dot get token length, and then you pass the compressed context. Fantastic. I think this is what I need. Now let's just print it. So print, and I'm gonna pass my compressed context, and then I'm gonna pass print. Let's pass some whoo, let's pass some hash here just to make some separation. Oh, you can see the model has been downloaded and loaded. So let me just get this. Let me just get this. Let me get this. Let me see if this gives me any error. No, perfectly fine. So we are printing till now. We didn't get any error, which is fine. Now the next is so complete context. Let's print something so you can understand. So original tokens. This is my original tokens, and in this I'm gonna pass my original. Show me. Okay, fine. Original tokens. Then we have our compressed tokens, and then let's ratio. Correct. Compressed ratio, which should be f, and then original tokens divided by compressed tokens plus not 1. Let's keep it till 5. So 1e minus 5, and then 2, excuse me, 2f, and then let's keep x, which will basically denote that what is the ratio of that. Okay, now compressed tokens, blah blah blah, original tokens divided by compressed tokens. It says invalid compression, compressed ratio to f of original tokens divided by compressed tokens plus 1 e minus. Okay, I have done something wrong here. Now you can see, if you see the result what we get, it says what should I, let me just close this, we don't need it. Okay, what should I do next? This is your compressed context. So this is the compressed context that we have, and based off this, your original tokens was more than 10,000, more than 10k, the original tokens. Now the compressed tokens is only 275. This is the compressed tokens, but it still holds your context, the contextual understandings and the meaning of your context. And based on this, now we'll feed it to a large language model and say, okay, now generate the response. And then we'll compare if the answer is same, which is RISD, the road, school, island, or whatever that we school that we have, right? Now original tokens, you can see 10x, the compression ratio is 38x time better. So what we are doing here, guys, it's not only about the query that you feed as a prompt, it's also the context. So we're also looking at how to compress the context, compress your query prompt, combine together, and then get your output. That is fantastic. Right now let's guess that. So here what I'm going to do is response equals, in the response I'm saying synthesizer dot synthesize, and I'm going to pass my, excuse me, I don't know what it's right now, synthesizer or synthesize. Oof. Okay, here I'm going to pass my question and then new retrieved node. Okay, so new, show me new retrieved nodes. Fantastic. And then I'm going to pass print response. Here you go. The author went to RISD for art school. This is what you need. That was your answer. Now you can see this is, and let me also do it through retriever query engine from argument. So let me just do end to end. So retriever retriever query engine equals, and I'm gonna say retriever query engine, not that. Okay, excuse me, it's becoming too smart. Okay, retriever query. I'm gonna use from args. Okay, so from args, and I hope this is right. Okay, from args, I'm gonna pass my retriever and then node post processor. I need a node post processor. Yes, this is right, correct. Now here I can pass this as a list. In the list, I will also pass that because that's my variable name as well. So node post processor. Okay, I don't need anything else. Fine. And now let's put our response here as well. So response equals, I'm gonna say retriever query engine dot query and just pass the question which is right. And now let's just print the response. If our answer is also right for this, you mean that we achieved what we wanted to do. So print string response. This is both more end to end. Okay, here you got the response already. The author went to RISD for art school. And now let's just print this. Once I print it, you will see the same answer. The author went to our. So what we did in this video, guys, so far, that we compressed original tokens more than 10K to something 275 and still got the same answer. What I'm all trying to say is that you should not, of course, do it where if you are really working in a regulatory industry where if you give any wrong answer it becomes a problem, or the if your reputation of the company goes for a toss, right? But this is helpful mainly for different type of knowledge bases that you have built internally, where you just retrieving the same response again and again, and you are just retrieving some historical data for your internal operations within your organizations like HR, marketing, sales, blah blah blah, right? So here we are doing is that we are compressing the prompts using long LLMLingua or LLMLingua of Microsoft, where that's a great project done by Microsoft to make it open source. I really loved it, and I hope you liked this video. This is what I wanted to create to help you understand how you can do it programmatically using Llama Index, because that integration has been done already. We'll also do a couple of more videos on this for the coding exercises, how you can use code related data to also compress and optimize those. Okay, optimization are the right way. Compression is something that will focus. Optimization is again a bit different than compression, by the way. Now, this is what I wanted to do in this video. I hope you liked it. If you like the content, please hit the like icon, and the code will be available on my GitHub repository. I'll give the link in description. If you have any comments, thoughts, feedback, please let me know in the comment box. And if you're getting stuck anywhere, you can also reach out to me through my social media channels. It is available on the YouTube channel banner and also the channel about us. That's all for this video, guys. It's already 3 in morning. I wanted to create this video. I hope you liked it, and share the channel and video with your friends and to peer. Thank you so much for watching. See you in the next one.